welcome. Hope you're doing well this morning. And I wanted to welcome our next speaker. We have Yoav Weiss. He's a security researcher with the Ethereum Foundation. And his talk is titled, AA is Easy If You Don't Care About Decentralization. Thank you.
Right. Hi, everyone. So many of you probably heard me talk about account abstraction before, and usually I talk about use cases, but I often get asked about the complexity of ERC 4337 and why does it have to be so damn complex. So today I'd like to say a few words about that. Of course, we won't be able to go into the full depth of the protocol, but I want to give you a glimpse. Now, before we start, let me tell you a little story about a monkey. So I have a monkey NFT. I really like it. It's really nice, and it's a really nice monkey. But it's worth a lot of money, so I want to sell it. And now I'm asking myself, why do I need this? Why do I need Ethereum, this complex blockchain, in order to trade my monkey? It's just, there's like complex data structures like Merkle trees. We have many staked validators with slashing conditions, and we have a complex DHT protocol for peer-to-peer communication. We have multiple client architecture. Why do we need all that? Why don't we just use a centralized web server and get it over with? Well, it turns out that the answer is that if we are serious about the monkey being my monkey, then we do need this complexity. If I was okay with trusting some server operator who may decide to take my monkey or to prevent me from selling it to someone, then I wouldn't need a blockchain. But it turns out that the community values things like self-custody and censorship resistance. So with that, let's talk about accounts. So smart accounts are basically smart contracts that let me implement functionality into my account, my on-chain representation. But there's a problem. With an EOA, I can communicate with the network. I can transact on the network directly. The EOA pays for the gas. I just sign a transaction. The EOA pays for the gas, and stuff gets executed. With a smart account, it doesn't work that way. And you actually need a funded EOA that will sign a transaction to pay for the gas and make a call into the account. And that's a big UX problem, because we cannot require users to have both a smart account and an EOA with some ETH, and then require them to sign each transaction twice, once for the EOA to pay for the gas and once for the real transaction. That's a UX that's not going to fly, and we'll never be able to get the next billion users. So with that, there's the centralized approach, which is what some projects tend to use for smart accounts. And it means that there is a centralized server. The server has a funded EOA that can send a transaction, and so I send my transaction, I send my operation to the server. The server wraps it in a meta transaction and puts it on chain for me, pays for the gas, and I compensate it like later. But or maybe I do, maybe I don't. Now the problem here is, as I said, it's not really self-custody. If I need somebody else's server to interact with my account, is it really my account? I would say not really. It's not, if I cannot use the account directly, maybe it's not really self-custodial. It's not really mine. It's only somewhat mine. And some people say that's not a big problem, and in many cases it isn't, until it is. Like, what happens if the wallet company runs out of money, it goes bust, and stops paying its AWS bill? So suddenly the server goes down, and I can no longer interact with my account. I'm stuck. Or maybe they get a denial of service attack against the server, and also I cannot interact with my account suddenly. Or maybe they work just fine. The server works just fine, but their business model changes to extract MEV. So they front run every transaction that has value, and they are going to win 100% of the time. I have no way to defend myself because they are actually the ones sending my transaction on chain. And of course, they could censor me because someone coerces them to do so. I mean, the server is operated by humans. They can be coerced. And there's the issue of privacy, because the server knows my IP address, so it has my real identity, and it sees all of my transactions, and maybe it keeps logs and shares them with someone, I don't know. So having a centralized server is not very good for self-custody. Now, so let's try to naively solve this problem. One way to do it is say, let's have many servers. What if the wallet company runs multiple servers, not one? Well, that doesn't change anything, because the servers are still operated by the same entity, so they would go down together, or they would censor together, or front run me together. So it's like one server. So the next logical step would be, let's make it a decentralized and incentivized network of relays. And then it's no longer operated by one entity, and problem solved. Well, we try that with, this is what we did with GSN, with the gas station network, and it does decentralize access, but there's a catch. There's a catch, because what if the account behaves inconsistently? The account could, when in an off-chain simulation, the account would appear to be compensating the relay, but when the relay puts it on-chain, it actually doesn't compensate, because it can detect that it's running on-chain by looking at some environment opcodes. So it decides not to pay, and now now the relay gets griefed. So we need to protect the relay against griefing. Now, how can the relay protect itself? We'll again try some naive approaches. What if the relay keeps a whitelist of known account implementations that don't grief it, and the relay only accepts these account implementations? So that's fine, but then who gets to decide what account implementation is legitimate and says that everything else is not? So it's permissioned in the sense that innovation is now permissioned. So instead, what if we restrict users? We say you can use any account implementation, but you have to sign in with your phone number, so the server can identify you. And then if you grief the server, they're going to block you. So this brings us back to censorship, because if they can block you for griefing, they can also block you for any other reason. So what if instead we say we don't require usernames and we don't require implementations. Instead, we keep a reputation for each account. That doesn't work because of Sybil. You're going to have Sybil attacks. Any attacker can keep spinning up more accounts and keep griefing the server. So what if the server, after simulating and seeing that the transaction pays, it will use flashbots to submit the transaction, and will not. So it will use flashbots and ask the flashbot relay to only submit the transaction on chain if it ends up paying. So now the DOS vector moves to flashbot itself, because the attacker is going to send an ongoing, is going to keep sending transactions that behave inconsistently. So the all pass simulation gets submitted to flashbots, but then flashbots ends up not including them because they don't pay, because they revert instead. So after a while, the flashbot relay that is now doing a lot of unpaid work is going to block this server, which brings us back to censorship. So now the entire server gets censored. So without taking all of these things into account, we cannot build a robust and permissionless solution. Either it has to be permissioned, or it's going to be vulnerable and be taken down by someone. Either way, we don't end up with a censorship-resistant solution. So that's what ERC 43.7 aims to solve. ERC 43.7 is account abstraction without compromising decentralization, which means that there are no centralized components, nothing is permissioned in a network, And the account is fully abstracted, which means that account validation involves executing EVM code, and this enables many attacks. It can lead to many denial of service vectors, which we need to address. So the protocol has to take care of all of these requirements, or else, if any of these requirements is not met, we're going to end up with a network that can censor users, or with no network at all because it will be attacked. But if we can make it, if you can make the network have all of these properties, then we end up with a robust solution that we can count on and not have any censorship vectors. So how does ERC-4337 achieve all that? The first thing we had to do is we had to separate validation from execution. The transaction has to be structured in a way that we know what part is the validation and what part is the execution. And then we can limit the amount of work. This is really the bare minimum we have to do. We have to limit the amount of work that has to be done in order to validate a transaction. If we don't do that, then the server may end up doing an infinite amount of unpaid work and never get to do any paid work. So we can say that even if the transaction is 5 million gas, it can only use 200K of gas for validation. And this limits the amount of potentially unpaid work. But that's only the start of it. Now, if a transaction is valid in the mempool, it gets propagated in the mempool, which means that every node in the mempool performs some work in order to validate it. Then we need it to also be valid with high likelihood to be valid on-chain, because otherwise, again, we get a denial of service vector. So, for example, suppose I implement an account that has a check for block number, and it says if the block number is even, I'm going to accept the transaction. If it's odd, I'm going to reject it. Now we have, so now during simulation, during an odd block, during an even block, it will be successful, so it will get propagated in the mempool. But then when someone tries to put it on chain in the next block, it's going to fail and not pay. So we needed to prevent that. In order to do that, we had to ban all the environment opcodes during validation. Note that all of these restrictions are only in validation. During execution, you can do whatever you want because you're already paying for it. But until you pay for the transaction, you cannot look at something like block number. You don't really need block number in order to validate any signature scheme. So that's one type of restrictions. Another issue is mass invalidation by flipping a flag in storage. What if I have many accounts that all check a flag in some singleton contract, and then I send 10,000 transactions to these accounts, but I front run my transactions with one transaction that flips the flag and invalidates all of them. So now at the cost of a single S-store, as a single state change, I invalidated 10,000 transactions, and I caused every node in the mempool to first have to process these transactions and not get paid for them. In order to prevent that, we needed to limit the storage access, but storage access is useful. You need, for example, to access your keys in order to validate them. So the account is allowed to access its own storage and its associated storage, which means storage that is associated with the account's hash in other contracts, such as an ERC20 balance for that account. But it means that two accounts cannot access the same storage slot during validation, which brings up the cost of the attack to order of n. Now you have to write to n slots to do n S-stores in order to invalidate n transactions. Another issue is the transactions cannot be mutually exclusive, because otherwise I can have many transactions, all of which are valid during propagation, but when you try to include them bundled together in the same block, they invalidate each other. For example, they could invalidate each other because during execution they can actually access anything. So what if transaction 1 passes validation, and then during its execution, it flips a flag in the account of transaction 2. And now transaction 2 that was formerly valid becomes invalid. So you can send any number of such mutually exclusive transactions, and the block builder will never be able to produce a block. To prevent that, we have to run all validations before any execution. So even if it's going to revert later because of then it will revert after paying. We have some global entities in the system that sometimes do need to access the same storage slot during transaction. For example, paymasters. The paymaster pays for the transaction for multiple transactions, multiple accounts, and it needs to access the same slots. In this case, we need to have a reputation for it, so if it causes too many invalidations, we're going to throttle it, and it will not cause a lot of unpaid work. But this requires Sybil resistance, because otherwise someone can keep spinning up more paymasters. So if the paymaster needs to access its own storage, it's like a global storage, it has to be staked. The stake is not slashed in any case, it's just used as a Sybil resistance mechanism. So I'm going to skip a bit because we're running out of time. Now, why does it have to be a standard? Why do all the bundlers need to implement, all the bundlers in the mempool need to implement the same restrictions and not come up with their own protection? The answer lies in spam protection. Bundlers need to, nodes in the mempool have to protect themselves against spam, against nodes that keep sending them invalid transactions. So, because this consists of this is unpaid work for them. So, if one node considers something to be valid, it propagates it to another node that considers it invalid, it will have to block the first node as a spammer. So, if they don't implement exactly the same rules, the network will get fragmented. Different parts of the network, different implementations will block each other, and we'll end up with many small mempools. Now that's a problem because having many smaller mempool is much more prone to censorship attacks. It's a smaller group of the transaction ends up in a smaller set of nodes. And also it means that we lose the benefit of multi-client architecture. Currently we have many bundler implementations, but if each bundler implementation had its own mempool with different rules, it means that a bug in one client can censor transactions. So, and of course we lose some economic security because bundlers are less profitable. They only see a subset of the transactions. So we have many reasons to have the same rules for everyone. This keeps the mempool more robust. Right. So the solution here is to have exactly the same implementation, exactly the same rules for all implementations, and we needed to do the same with Ethereum because of the multi-client architecture. So Ethereum has very clear specs for the very clear consensus specs. And we do a lot of testing and fuzzing to cover that. And ERC-457 does the same thing. So just to summarize, since we're running out of time, we have, so account abstraction could be really easy if we didn't care about censorship resistance, which is exactly the same reason we use the blockchain, because we do care about these values. So smart accounts shouldn't have to care about decentralizing, about that. They should focus on user value. So ERC-437 does it for them as long as you use bundlers that are compliant with the protocol and participate with the mempool properly. Right. So I think we're out of time, so thank you. Right, do we have time for questions or no? Okay.